Good day, friends. Right now, let's try to solve this problem. A hemisphere of mass 100 grams lies on a horizontal surface. From its top point, a pack of mass 10 grams slides down without friction, starting from rest. Due to friction between the hemisphere and horizontal surface, the hemisphere starts to move when the angle is at 10 degrees. Find the coefficient of friction mu. Okay, if we imagine it, it would be something like this. We have two blocks, yeah? This thing is a huge block, and this thing is a small block. And while this thing, well, at the very beginning it starts here, and while it is on 10 degrees, when this alpha gets 10 degrees, this huge block experiences some force horizontally. Exactly, we know that this is, we have here components of the normal force, yeah, because it pushes up and this thing pushes down as well, and it has two components which are vertical and horizontal, and its horizontal normal force starts to push this object here, yeah, and as it pushes, exactly, this thing starts to move. However, we need to mention that there is no friction between this huge block and the small block, but there is a friction between this huge block and the ground. Okay, so this is a small analysis for our problem, but let's make it a little bit more detailed and more physical, right? Okay, so what do we have here? What do we have here? Well, we have, well, first of all, let's try to find what we need to find. And this thing is the most important thing for us. This is the mu, coefficient of friction between the ground and our huge mass. Okay, but we need to understand one thing. When this object is at 10 degrees, when this is 10 degrees, this object only starts to move. But in fact, it didn't start to move. It just will start to move. So at the instant, if we just look at the frame, then this thing will not still accelerate. So the acceleration would be 0, which means that the force pushing this object, for example, to the left, will be equal to friction force, which is directed opposite side. This is really important to note, okay? So what do we have here? Let's try to write down forces, yeah? Show the forces which are acting on our small block. Basically, we have here mg, yeah, definitely. We have here, yeah, our normal force. Let's call it normal force 2, yeah? Because normal force 1 would be the normal force of the huge object, yeah? And what else? There is no friction, and I believe that's it. Yeah, there is nothing else which is acting on our object. We know that this thing is gonna go in circle, something like this, angular velocity. And if this is angular velocity, if this thing goes in circle, we know there is something, one more thing which is really important. It's the centripetal acceleration. So this thing is gonna go to the center, yeah, strive to the center. It would be the centripetal acceleration would be directed inward to the center. Okay, good. This is analysis for the small block. Let's make some analysis for huge block. Yep. So let me write it something like this. This would be our centripetal acceleration here. Okay. Our ordinary acceleration, which is the motion of this huge block, is 0, but in fact it tries to go there, because right now I will show you why it tries to go left. Basically, if our huge object pushes this small object upward, it means the same thing happens opposite side. So this small block tries to push this block opposite direction, somewhere here. This would be our normal force 2. These two forces would be equal to each other, right? Okay, normal force 2. What else is acting? Well, from the bottom to the top, we write here normal force 1, which is the normal force of the huge object. Yep. What else? It has its own, from the center of mass, let's put it somewhere here. We also have here huge mg. And as you can see here, well, vertical forces cannot push our object horizontally. So N1 and huge mg cannot act on our object to push this thing to right or left at all. But the thing about the normal force 2, it has two components. Yeah, it has vertical component and horizontal component, which is directed left side. That's why our acceleration is directed left side, because it tries to go left. However, at the instant, it still does not start to move. That's why this is really important. What else? If this thing tries to go to the left, it means that in fact something stops it at the instant, which is our friction force. Yeah, this is our friction force. Okay, that's good. I think that it's pretty much all. And right now, let's write down equations, Newton's second law, and let's see, maybe we can find this thing. Okay, first of all, this is the formula of Newton's second law. The sum of forces must equal mass multiplied acceleration, right? Okay, good. Let's write with red one. So if we have normal force 2 going to the right top side and mg straight down, it means that we can choose xy component like this. So if this thing's going to be our y component, this is going to be our x component. And that's why we need to make something like this. Well, if this thing is alpha, it means we can use the law of z, which is like this. If this angle is alpha, this angle is alpha as well. This is alpha. Okay, so let me bring it back. Yeah, this would be alpha as well. And this will have two components, which are here, it's mg cosine alpha because it's adjacent. And the second one, which is moving our object, here is mg sine alpha. Yeah, that's why it slides down in that direction. Okay, so this force, let me draw something with green probably. Yeah, it would be mg cosine alpha, mg cosine alpha. Good. And we have our centripetal acceleration. That's why let's write it down. Mg cosine alpha will be the main character here, yeah, because it is the same direction with our centripetal acceleration. Mg cosine alpha. N2 tries to oppose it, as you can see it here. N2 tries to oppose it, and this would be our small m AC. And we know that AC is just what do we have here? We have here, well, basically we don't have any centripetal acceleration. We don't have any kind of tangential velocity. Do we have anything like angular velocity? Do we? I think we don't. Yeah, we have here mass, small mass, alpha angle, and we need to find mu. Okay. Yeah, for right now, let's write it something like this. It would be enough for us. What else? Let's try to write it something like this. Let's open this up. We have m, and AC opens like what? It opens like v squared divided by r. Yeah, and this thing would be tangential velocity. However, what can we do with this? Let's look at this part. So as I told you before, at the very beginning we start from here, and then we appear to be here, right? So in this process, this thing this huge object has got to be just totally static. It does not move at all, and it just starts to slip off. It starts to move only when this thing appears to be at 10 degrees. Okay. So what is important about this part? We can see this thing has a change in height, which is exactly what we can write down here, the equation for energy conservation. So basically, at the very beginning, we had this object here. It had a maximum height, and then it lost its height. This thing would be the difference in height. Yeah, this part. Let me show it with green. This part would be lost in height. But what is exactly lost in height? We know that we cannot have a loss in energy. It means that this lost height gives us velocity. In here, we have this velocity. Velocity in here would come from the lost height, from delta H. Yeah. Let me write it with V. Okay. So that's why we can here write down something like this equation for our object's energy. It would be m. Yeah. Let me write it like this. Yeah. Mg delta H equals mv squared divided by 2. Why delta H? Why delta H? Because only loss in height. Yeah. Loss in height gains us this velocity. Gains velocity. So if we don't lose any height, it means that we cannot gain any velocity. Velocity appears from the loss in height. Okay, that's why we need to write down here delta H. So what is our delta H? We don't know, but in fact we do know why. Because if we say that this entire part, let me choose some different, probably this violet. If this entire part is R, if this part is R, this part is also still R, right? So in perspective of this second R, and this is alpha, we know that this part would be r cosine alpha, right? From perspective of this radius. This entire thing would be radius, right? Okay, it's this one. But from perspective of this second radius, this would be r cosine alpha because it's adjacent again, right? Okay, so this small delta H, the change in height, would be this entire radius minus r cosine alpha, right? This entire part minus this part. That's how we gain our change in height. Okay, let me just take all this off the way, yeah, and yeah, like this. Yeah, good. Delta H would be, let me continue it here, mg, delta H would be r minus r cosine alpha. It's the same radius, that's why, yeah. So it's still mv squared divided by 2. Yeah, we can cancel out these m's, and we can say that r comes out because it's the common factor. Yeah, it's going to be 1 minus cosine alpha. Good. And we have here v squared divided by 2. But let me write down, let's move this 2 to this side, so that's why it will become v squared equals 2gr, 1 minus cosine alpha in brackets. Okay, so I will not try to find v itself. Yeah, v squared is enough to me. Why? Because I can put it right here. We have also v squared. That's why, yeah, right. Let's write it something like this. Mg and delta H no, mg cosine alpha. Yeah, I'm sorry, mg cosine alpha. We are looking at this thing. Yeah, minus n2 equals what? mv squared divided by r, but m divided by r, v squared is our this thing, 2gr1 minus cosine alpha. Yeah, and right now we can just take this r's off. That's how we have something like this. Mg cosine alpha. Let me bring of this thing to this side and this n to this side, and that's how we get something like this. It would be m, yeah, minus m 2m 2mg. Yeah, and let me open the brackets, 2mg minus 2mg cosine alpha. Okay, so what I did, I just took this thing, these three things, and I've made just this thing. Yeah, I multiplied to each one of them. Yep, okay. So, and that side would be just n2. That side would be n2. Yeah, good, good. And as you can see here, have a common factor of 3 mg's. Yeah, so I shouldn't have moved mg. Okay, that's not a problem, to be honest. We just take mg from here. This would be cosine alpha, and what? Oh, no. Yeah, this was correct. So right now what we have here, this thing would be plus. Why? Because it's minus, goes to that side, it's minus, and it would be plus inside of the brackets. Yeah, so this thing is going to be, this is good. Yeah, I made a correct thing. This would be 3mg cosine alpha minus 2mg. Yeah, and this would be n2. And right now we can take mg out of, and it would be 3 cosine alpha minus 2. Yeah. That's good. That's good. I like it. I like it. Yeah. This is the very important thing. I believe this would be our final result for N2. However, let's try to implement it for our final result. What do we have for the huge block? It's the analysis of the small block only. What about a huge block? Well, vertically, it does not move at all. That's why I can write down here N1. Let's write down it with blue because we started with blue. Yeah. So it would be just N1 equals mg, huge mg, right? No, not correct. Why? Because this mg, huge mg, also has a help of this N2. Yeah, because they are directed to the same side. So this thing is going to be what? If this is alpha, this is n2 cosine alpha. n2 cosine alpha adjacent again, okay? Plus n2 cosine alpha. They have help of each other. m2 pulls downward, n2 cosine alpha pulls downward, n2 cosine alpha, and n1 pulls upward. However, they are in equilibrium vertically. That's why we can say that n1 equals huge mg plus n2 cosine alpha. It does not move vertically. Yeah, what about the horizontal motion? Horizontal motion does not appear at this instant. So it's just at the start of slipping. It's only is going to move. So it still didn't, in fact. It just is going to. That's why we say that acceleration in horizontal point is 0, because it's not in fact 0. It's going to start, but it still didn't. So it's at the end of this process. But still, it's still that process. Yeah, acceleration being 0. But right now, it's just going to become something else than 0. It's going to increase. Yeah, but at this instant, it still didn't. The force which is going to move this thing is this horizontal component of the normal force. It is n2 sine alpha, right? It is n2 sine alpha, and the force is opposing is friction force. And as you can see here, friction force would be just 0 because ma. Yeah, if we write here ma and our a is 0, is going to be just all this side is going to be 0. And if this side is 0, I can move this thing here, and it would be just plus from another side. So it's going to be something like this. Yeah, n2 sine alpha equals F friction. Okay, good. And let's define this F friction. So what is the problem about friction force? We have two types of friction force, which are static friction, and kinetic friction. So in kinetic friction, we have this thing. We can say that in kinetic friction, friction force equals mu n. Yeah. However, the thing about static friction, it's something like this. Friction force is less or equal to mu n. So it would be always, at most of the situations, less than mu n. However, when it can be equal, at the moment when it's maximum. So what does it mean? What does it mean that F friction, static friction, let me write it, yeah, Fs, static friction, when it would become equal to mu n at the situation when this thing becomes maximum, when this thing tries to slip off. And that's the thing that is going to happen in our situation. This thing starts to, it is going to start to move. What is that this thing is going to change from static friction to kinetic friction. And that's how we can equalize our friction force to mu n, because it's the final moment of the static friction. Okay, so that's how right now we can say that n2 sine alpha equals mu n. And what is the n for our object? It is n1. It is n1. Okay, and we can see that our n1 is huge mg plus n2 cosine alpha, and we can write down this thing in here. However, let me do something like this. We need to find this mu, right? So what I am going to do is something like this. So mu n2 sine alpha from above, n2 sine alpha above here, and n1 below. Yeah, that would be good. That would be good. And right now, let me put that n1, this n1 instead of this thing instead of n1. Yeah. Okay. So it's going to be mu equals n2 sine alpha, and below we have something a little bit long, which is huge mg plus what? n2 cosine alpha. Okay, good. n2 cosine alpha. And we do know this mg is constant, sine alpha and cosine alpha, it's 10 degrees. Only thing that we don't know here is what it is, this thing, n2. And if we look at here, we can see that we have n2. That's why we can write something like this. Mu equals to what? Let's put this mg 3 cosine alpha minus 2. Yeah, mg 3 cosine alpha minus 2. Is it correct? Yes, it is. And sine alpha outside. Here we have huge mg plus n2. Again, the same thing, mg 3 cosine alpha minus 2 cosine alpha. And what can we do? We can just take this g as a common factor outside, but if we take it, we can just cancel these things. Yeah. So our final result will probably be this thing, m3 cosine alpha minus 2 sine alpha. And here we have m plus m small 3 cosine alpha minus 2 cosine alpha. Yeah, I guess this is the correct answer. Yeah. And yeah, basically sine alpha divided by cosine alpha, we can just write it as tangent alpha, but it does not matter, to be honest. It's the same thing. So this would be our final result. This is the answer. And let's see, yeah, we have this small m, we have this huge m, we have alpha, sine alpha, 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 because it's just 10 degrees. Yeah, basically you can put numbers inside and then see what result you have, but I will not do it because I think that this is more than enough just doing the physics part, and this is the correct answer. So if you have any questions, you can write me privately. Thanks for your attention. Goodbye.